Hello, welcome to section 3 of chapter 5. In the first two sections we've talked about how to simplify polynomials by adding, subtracting, and multiplying and dividing, and we've also talked about exponent rules. Now we're going to jump in and talk about polynomial functions, or basically f of x is equal to a polynomial, and we're going to talk about what those graphs look like. We're going to talk about how to evaluate those functions, the vocabulary that goes with them, and so on. So on your vocab sheet, on your note sheet, you have this list of vocabulary. So you might want to just make sure as you go through that you jot down a definition, or make sure that you know what each of these means so that when they appear in problems or in class discussions, that you understand what it is that we're talking about. Okay, so we're going to start by talking about a polynomial in one variable. A polynomial is an expression that looks like this. And this looks much more complicated than it is. Basically, a sub n is a number, it's a constant, times x to some power n, plus a to the n minus a sub n minus 1. That n minus 1 just identifies the next coefficient, and then x to the n minus 1. So notice the original power was x to the n, the next power is n minus 1, so it goes down a little bit, and so on all the way down until we get to the constant term. So for example, we can look at some of our polynomials down here in this chart to see what those would look like. We call our polynomials written in standard form when I put my exponents in descending order. That means that I need to start with my biggest exponent and go all the way down to my constant term, which has a degree of 0. The degree of the polynomial is the biggest exponent, like we've talked about before. And this coefficient here, this a sub n, the coefficient of that term with the biggest degree, is called the leading coefficient. So some of our polynomials have different names. For example, a constant is just a plain number. That's technically a polynomial. So the number 12, it has a degree of 0 because you could think of this as being like times x to the 0, but x to the 0 is just 1, so that's the same as 12. And the leading coefficient is the only number there is, which is 12. Linear functions we've talked about earlier this year, 4x minus 9. This is standard form because it's in descending order, so I have x to the first in my first term and x to the 0 in my second term. The degree is 1 because that's the biggest exponent on a variable, and the leading coefficient is 4, the coefficient of the term with the biggest degree. Quadratic functions we also talked about in chapter 4. Those are x squared. So here my degree is 2 and my leading coefficient is 5. Notice again, the exponents are in descending order, x squared, x to the first, x to the 0. So this is in standard form. Cubic is a polynomial with the biggest exponent of 3. So in this case, the degree is 3 and the leading coefficient is 8. And that pattern continues. We call polynomials of 4th degree quartic, and we call polynomials of 5th degree quintic. So for example, I could have 3x to the 4th minus 10, and I could have negative x to the 5th plus 3x to the 4th minus x cubed plus x squared minus 0, or minus 10, let's say. Right? So in this case, the degree would be 4, and the leading coefficient would be 3. Here, the degree would be 5, and the leading coefficient would be negative 1. So that's some of the vocabulary we need for polynomials. So let's look at this expression, 7z cubed minus 4z squared plus z, and we're going to talk about the degree and the leading coefficient. If it is not a polynomial in one variable, we're going to explain why. Well, in this case, this is a polynomial in one variable. The only variable is z. There are no variables in the denominator, no variables with negative exponents, no variables under square roots. So here the degree is 3 because that's the largest exponent. And my leading coefficient then is the coefficient of that term, which is 7. Let's take a look at this one. 6a cubed minus 4a squared plus ab squared. This is not a polynomial in one variable, okay? And in this section, we are studying polynomials of one variable and how their graphs act. This includes a and b, so even though it meets all of the other rules, there are no variables with negative exponents, no variables under a square root, no variables in the denominator. Even though it meets those and all of my exponents are positive integers as well, It has two variables, so it's not a polynomial in one variable. Take a look at this one. 3x to the 5th plus 2x squared minus 4 minus 8x to the 6th. If we want to look at this better, we should write it in standard form. So I'm going to take my term with the largest degree, x to the 6th, and write that first. And I'm going to write everything in descending order, so I have my exponents in descending order. So this is a polynomial in one variable. The degree is 6, and the leading coefficient is -8. All right, I'm going to have you guys try 3 in a row here. Okay, for this one, the answer should have been B. Look at this one. This one is not a polynomial in one variable because it includes x and y. And this one, the answer is B. The degree here is 7. That's the largest exponent, and the leading coefficient then is -5. All right, a polynomial function, which is really what we're getting to in this section, is a continuous function, so there's no breaks or holes or anything, that can be described by a polynomial equation in one variable. So for example, f of x equals 3x cubed minus 4x plus 6. That would be a cubic polynomial function. The simplest ones only include the first term here, which would be a coefficient times x to some power, so like 2x squared, or -5y cubed, or something like that. Those are called power functions, and they're the simplest kind of polynomial functions that we can have. Just like with any other function, we can evaluate polynomial function. If we know an element in the domain, we can plug it in, and we can get the corresponding value in the range, meaning that if we know x, we can plug it in, and we can get our y value, or our f of x value. So that's what we're going to try in the next couple examples. Here, they're showing us how polynomial functions are used to model real-life situations. In this case, this function is modeling the volume of air in our lungs during a 5-second respiratory cycle. So the volume with regards to time is this function. V is the volume in liters, and T is the time in seconds. Okay, so if we want to find the volume, so volume is going to be our unknown, 1.5 seconds into the cycle. So 1.5 is seconds, that means it's time, so we're going to substitute 1.5 in for t, and then we're just going to evaluate. This is one where you would be able to use a calculator. So we plug 1.5 in to each of our places where we see t, and we do those calculations, and then we add and subtract. Notice here that they're putting the approximation sign because they had to round these to the nearest. Most of them they round to the nearest 10,000th. This one they rounded to the nearest 1,000th. This gives us 0.4766. And since that is an answer that is volume, your units are super important. Your units here are liters. So there would be 0.4766 liters of air in the lungs after 1.5 seconds. Okay, you guys try this one. All right, hopefully you got A, 11.6 meters. And again, in this case, 1.25 is time in seconds, and we're plugging that in to get the height of a toy rocket. So you would plug in like this, use your calculator to simplify, and you should get 11.6 meters. You have to have your units. Okay, let's look at this example. In this case, we're still evaluating a polynomial function, but notice that we are plugging in variables instead of just regular numbers. So notice here they give me my function, right? B evaluated at m equals 2m squared plus m minus 1. That's my basic function. They want me to find this. B, remember this is not b times 2x minus 1. This is the function b evaluated at, or b of 2x minus 1, minus 3 times b evaluated at x. So we're going to replace the m here with 2x minus 1 for the first part. So there's my original function. I'm going to take out the m, and I'm going to replace it with 2x minus 1. So I have 2 times 2x minus 1 squared plus 2x minus 1 minus 1. And when we simplify that, we get 8x squared minus 6x. Remember that this 2x minus 1 quantity squared means 2x minus 1 times 2x minus 1, so you have to FOIL. Then we're going to evaluate 3 times b of x. So I'm going to multiply 3 times my function, and I'm going to plug in x instead of m. So that gives me 6x squared plus 3x minus 3. Now I need to subtract those two things that I got. So b of 2x minus 1 was 8x squared minus 6x minus 3 times b of x was 6x squared plus 3x minus 3. And then we just simplify. Here they're distributing the negative, and then we're going to add and subtract like terms. And that gives me 2x squared minus 9x plus 3. All right, now I want you guys to try this one. All right, here your answer should be B. And there's the work if you need to check that out. Okay, let's talk a little bit more about what graphs of polynomial functions look like. The general shapes are shown here. This shows the maximum number of times that a graph can cross the x-axis. And that's always going to be the same as the degree. So for example, a constant function is a horizontal line. Its degree is 0. It never crosses the x-axis. A linear function has a degree of 1. It crosses the x-axis once. A quadratic function has a degree of 2, and the maximum number of times it can cross the x-axis is 2. But remember, we know that parabolas can also cross 0 times, like if they're floating below, or if just the vertex touches. Whoops, that was bad. Pretend that just touches at that one point. We know that that could happen, but the most x-intercepts it could have would be 2. Cubic functions have this general shape, and the maximum number of x-intercepts they can have is 3. Same with quartic. They have this general shape. And quintic. Again, their degree, quintic function has a degree of 5, is the maximum number of times that it could cross. But I could have a quintic function that looks like this. And so it would only cross the x-axis once, even though it's still quintic. All right, end behavior of polynomial functions is something that we're going to work on. And this depends on if the degree is even or odd. And it also depends on if the leading coefficient is positive or if the leading coefficient is negative. So if my degree is even, anytime the degree is even, both ends will always go the same direction. So they'll either both go up or they'll both go down. So this first column shows me even functions. Okay, if the leading coefficient is positive, it opens up, just like with parabolas, and if the leading coefficient is negative, it opens down. So this is the way we talk about the end behavior. The end behavior means what's happening off at the ends of my function. So notice, both of these ends will go positively to infinity. So we say f of x, which is the same as y goes to positive infinity as x goes either to negative infinity or positive infinity. So as x goes to negative infinity, as x gets really negative, what's happening to y? It's going up forever, so y is going to positive infinity. What's happening as x goes to positive infinity, as x gets really positive? Well, same thing. My function is moving up towards positive infinity. Whereas if it's flipped over the other direction, as x goes to negative infinity, y is going down to negative infinity. As x goes to positive infinity, y is going down to negative infinity also. Whereas if my degree is odd, the ends of my functions are always going to go opposite directions. So with my positive leading coefficient, you can kind of think of this as a function with a positive slope in a way. So it's going to, as x goes to negative infinity, y goes to negative infinity. And as x goes to positive infinity, y goes to positive infinity. It's the opposite when the leading coefficient is negative. You can kind of think of negative slope. As x goes to negative infinity, y goes to positive infinity. And as x goes to positive infinity, y goes to negative infinity. So let's look at one example real quick. Graphs of polynomial functions. Take a look at this graph. And here is how we would describe the end behavior. This is even because both ends go in the same direction. y is going to negative infinity as x goes to positive or negative infinity, and it never touches the x-axis, so it has no real zeros.